In physics, an inertial frame of reference, also inertial reference frame, or inertial frame or Galilean reference frame, or inertial space, is a frame of reference that describes time and space homogeneously, isotropically, and in a time-independent manner. All inertial frames are in a state of constant, rectilinear motion with respect to one another. An accelerometer moving with any of them would detect zero acceleration. Measurements in one inertial frame can be converted to measurements in another by a simple transformation, the Galilean transformation in Newtonian physics, and the Lorentz transformation in special relativity. In general relativity, in any region small enough for the curvature of spacetime to be negligible, one can find a set of inertial frames that approximately describe that region. Physical laws take the same form in all inertial frames. By contrast, in a non-inertial reference frame, the laws of physics vary depending on the acceleration of that frame with respect to an inertial frame, and the usual physical forces must be supplemented by fictitious forces. For example, a ball dropped towards the ground does not go exactly straight down because the Earth is rotating. Someone rotating with the Earth must account for the Coriolis effect, in this case thought of as a force to predict the horizontal motion. Another example of such a fictitious force associated with rotating reference frames is the centrifugal effect, or centrifugal force. Introduction. The motion of a body can only be described relative to something else, other bodies, observers, or a set of space-time coordinates. These are called frames of reference. If the coordinates are chosen badly, the laws of motion may be more complex than necessary. For example, suppose a free body, one having no external forces on it, is at rest at some instant. In many coordinate systems, it would begin to move at the next instant, even though there are no forces on it. However, a frame of reference can always be chosen in which it remains stationary. Similarly, if space is not described uniformly or time-independently, a coordinate system could describe the simple flight of a free body in space as a complicated zigzag in its coordinate system. Indeed, an intuitive summary of inertial frames can be given as, in an inertial reference frame, the laws of mechanics take their simplest form. In an inertial frame, Newton's first law, the law of inertia, is satisfied. Any free motion has a constant magnitude and direction. Newton's second law for a particle takes the form with F the net force, a vector, and the mass of a particle, and the acceleration of the particle, also a vector, which would be measured by an observer at rest in the frame. The force F is the vector sum of all real forces on the particle, such as electromagnetic, gravitational, nuclear, and so forth. In contrast, Newton's second law in a rotating frame of reference, rotating at angular rate about an axis, takes the form which looks the same as in an inertial frame, but now the force F is the resultant of not only F, but also additional terms. The paragraph following this equation presents the main points, without detailed mathematics. Where the angular rotation of the frame is expressed by the vector pointing in the direction of the axis of rotation, and with magnitude equal to the angular rate of rotation, symbol denotes the vector cross product. Vector xb locates the body and vector vb is the velocity of the body according to a rotating observer, different from the velocity seen by the inertial observer. The extra terms in the force F are the fictitious forces for this frame. The first extra term is the Coriolis Force, the second the Centrifugal Force, and the third the Euler Force. These terms all have these properties: they vanish when equals 0, that is, they are 0 for an inertial frame, which, of course, does not rotate. They take on a different magnitude and direction in every rotating frame, depending upon its particular value of. They are ubiquitous in the rotating frame, affect every particle regardless of circumstance, and they have no apparent source in identifiable physical sources, in particular, matter. Also, fictitious forces do not drop off with distance, unlike, for example, nuclear forces, or electrical forces. For example, the centrifugal force that appears to emanate from the axis of rotation in a rotating frame increases with distance from the axis. All observers agree on the real forces, F. Only non-inertial observers need fictitious forces. The laws of physics in the inertial frame are simpler because unnecessary forces are not present. In Newton's time, the fixed stars were invoked as a reference frame, supposedly at rest relative to absolute space. In reference frames that were either at rest with respect to the fixed stars, or in uniform translation relative to these stars, Newton's laws of motion were supposed to hold. In contrast, in frames accelerating with respect to the fixed stars, an important case being frames rotating relative to the fixed stars, the laws of motion did not hold in their simplest form, but had to be supplemented by the addition of fictitious forces, for example, the Coriolis Force and the Centrifugal Force. Two interesting experiments were devised by Newton to demonstrate how these forces could be discovered, thereby revealing to an observer that they were not in an inertial frame. The example of the tension in the cord linking two spheres rotating about their center of gravity, and the example of the curvature of the surface of water in a rotating bucket. In both cases, application of Newton's second law would not work for the rotating observer without invoking centrifugal and Coriolis forces to account for their observations. Tension, in the case of the spheres, parabolic water surface, in the case of the rotating bucket. As we now know, the fixed stars are not fixed. Those that reside in the Milky Way turn with the galaxy, exhibiting proper motions. Those that are outside our galaxy, such as nebulae once mistaken to be stars, participate in their own motion as well, partly due to expansion of the universe, and partly due to peculiar velocities. The Andromeda Galaxy is on collision course with the Milky Way at a speed of 117 km/s. The concept of inertial frames of reference is no longer tied to either the fixed stars or to absolute space. Rather, the identification of an inertial frame is based upon the simplicity of the laws of physics in the frame. In particular, the absence of fictitious forces is their identifying property. In practice, although not a requirement, using a frame of reference based upon the fixed stars as though it were an inertial frame of reference introduces very little discrepancy. For example, the centrifugal acceleration of the Earth, because of its rotation about the Sun, is about 13 million times greater than that of the Sun about the galactic center. To illustrate further, consider the question, does our universe rotate? To answer, we might attempt to explain the shape of the Milky Way galaxy using the laws of physics. Other observations might be more definitive, that is, provide larger discrepancies, or less measurement uncertainty, like the anisotropy of the microwave background radiation or Big Bang nucleosynthesis. Just how flat the disk of the Milky Way is depends on its rate of rotation in an inertial frame of reference. If we attribute its apparent rate of rotation entirely to rotation in an inertial frame, a different flatness is predicted than if we suppose part of this rotation actually is due to rotation of the universe, and should not be included in the rotation of the galaxy itself. Based upon the laws of physics, a model is set up in which one parameter is the rate of rotation of the universe. If the laws of physics agree more accurately with observations in a model with rotation than without it, we are inclined to select the best fit value for rotation, subject to all other pertinent experimental observations. If no value of the rotation parameter is successful and theory is not within observational error, a modification of physical law is considered. For example, dark matter is invoked to explain the galactic rotation curve. So far, observations show any rotation of the universe is very slow, no faster than once every 1012 years, 1013 Red/YR, and debate persists over whether there is any rotation. However, if rotation were found, interpretation of observations in a frame tied to the universe would have to be corrected for the fictitious forces inherent in such rotation. Evidently, such an approach adopts the view that an inertial frame of reference is one where our laws of physics apply, or need the least modification. When quantum effects are important, there are additional conceptual complications that arise in quantum reference frames. Background. A brief comparison of inertial frames in special relativity and in Newtonian mechanics, and the role of absolute space is next. A set of frames where the laws of physics are simple. According to the first postulate of special relativity, all physical laws take their simplest form in an inertial frame, and there exist multiple inertial frames interrelated by uniform translation. Special principle of relativity: if a system of coordinates k is chosen so that, in relation to it, physical laws hold good in their simplest form, the same laws hold good in relation to any other system of coordinates k moving in uniform translation relatively to k. Albert Einstein, The Foundation of the General Theory of Relativity, Section A, 1. The principle of simplicity can be used within Newtonian physics as well as in special relativity, see Nagel, and also Blagojevic. The laws of Newtonian mechanics do not always hold in their simplest form. If, for instance, an observer is placed on a disk rotating relative to the Earth, he/she will sense a force pushing him/her toward the periphery of the disk, which is not caused by any interaction with other bodies. Here, the acceleration is not the consequence of the usual force, but of the so-called inertial force. Newton's laws hold in their simplest form only in a family of reference frames, called inertial frames. This fact represents the essence of the Galilean principle of relativity. The laws of mechanics have the same form in all inertial frames. In practical terms, the equivalence of inertial reference frames means that scientists within a box moving uniformly cannot determine their absolute velocity by any experiment, otherwise the differences would set up an absolute standard reference frame. According to this definition, supplemented with the constancy of the speed of light, inertial frames of reference transform among themselves according to the Poincare group of symmetry transformations, of which the Lorentz transformations are a subgroup. In Newtonian mechanics, which can be viewed as a limiting case of special relativity in which the speed of light is infinite, inertial frames of reference are related by the Galilean group of symmetries. Absolute space. Newton posited an absolute space considered well approximated by a frame of reference stationary relative to the fixed stars. An inertial frame was then one in uniform translation relative to absolute space. However, some scientists, called relativists by Mach, even at the time of Newton, felt that absolute space was a defect of the formulation and should be replaced. Indeed, the expression inertial frame of reference, German, Inertialsystem, was coined by Ludwig Lang in 1885 to replace Newton's definitions of absolute space and time by a more operational definition. As referenced by Eero, Lang proposed a reference frame in which a mass point thrown from the same point in three different, non-coplanar, directions follows rectilinear paths each time it is thrown, is called an inertial frame. A discussion of Lang's proposal can be found in Mach. The inadequacy of the notion of absolute space in Newtonian mechanics spelled out by Blagojevic. The existence of absolute space contradicts the internal logic of classical mechanics, since, according to Galilean principle of relativity, none of the inertial frames can be singled out. Absolute space does not explain inertial forces, since they are related to acceleration with respect to any one of the inertial frames. Absolute space acts on physical objects by inducing their resistance to acceleration, but it cannot be acted upon. Milut and Blagojevic, Gravitation and Gauge Symmetries, page 5. The utility of operational definitions was carried much further in the special theory of relativity. Some historical background including Lang's definition is provided by de Salle, who says in summary, the original question, relative to what frame of reference do the laws of motion hold, is revealed to be wrongly posed. For the laws of motion essentially determine a class of reference frames, and, in principle, a procedure for constructing them. Robert de Salle, Space and Time, Inertial Frames. Newton's inertial frame of reference. Figure 1, two frames of reference moving with relative velocity. Frame S has an arbitrary but fixed rotation with respect to frame S. They are both inertial frames provided a body not subject to forces appears to move in a straight line. If that motion is seen in one frame, it will also appear that way in the other. Within the realm of Newtonian mechanics, an inertial frame of reference, or inertial reference frame, is one in which Newton's first law of motion is valid. However, the principle of special relativity generalizes the notion of inertial frame to include all physical laws, not simply Newton's first law. Newton viewed the first law as valid in any reference frame that is in uniform motion relative to the fixed stars, that is, neither rotating nor accelerating relative to the stars. Today the notion of absolute space is abandoned, and an inertial frame in the field of classical mechanics is defined as an inertial frame of reference is one in which the motion of a particle not subject to forces is in a straight line at constant speed. Hence, with respect to an inertial frame, an object or body accelerates only when a physical force is applied, and, following Newton's first law of motion, in the absence of a net force, a body at rest will remain at rest, and a body in motion will continue to move uniformly, that is, in a straight line, and at constant speed. Newtonian inertial frames transform among each other according to the Galilean group of symmetries. If this rule is interpreted as saying that straight line motion is an indication of zero net force, the rule does not identify inertial reference frames, because straight line motion can be observed in a variety of frames. If the rule is interpreted as defining an inertial frame, then we have to be able to determine when zero net force is applied. The problem was summarized by Einstein. The weakness of the principle of inertia lies in this, that it involves an argument in a circle. A mass moves without acceleration if it is sufficiently far from other bodies. We know that it is sufficiently far from other bodies only by the fact that it moves without acceleration. Albert Einstein, The Meaning of Relativity, page 58. There are several approaches to this issue. One approach is to argue that all real forces drop off with distance from their sources, in a known manner, so we have only to be sure that we are far enough away from all sources, to ensure that no force is present. A possible issue with this approach is the historically long-lived view, that the distant universe might affect matter's Mach's principle. Another approach is to identify all real sources for real forces, and account for them. A possible issue with this approach is that we might miss something, or account inappropriately for their influence, Mach's principle again. A third approach is to look at the way the forces transform when we shift reference frames. Fictitious forces, those that arise due to the acceleration of a frame, disappear in inertial frames, and have complicated rules of transformation in general cases. On the basis of universality of physical law, and the request for frames where the laws are most simply expressed, inertial frames are distinguished by the absence of such fictitious forces. Newton enunciated a principle of relativity himself in one of his corollaries to the laws of motion. The motions of bodies included in a given space are the same among themselves, whether that space is at rest, or moves uniformly forward in a straight line. Isaac Newton, Principia, Corollary, page 88, in Andromeda translation. This principle differs from the special principle in two ways. First, it is restricted to mechanics, and second, it makes no mention of simplicity. It shares with the special principle the invariance of the form of the description among mutually translating reference frames. The role of fictitious forces in classifying reference frames is pursued further below. Separating non-inertial from inertial reference frames. Theory. See also, non-inertial frame, rotating spheres and bucket argument. Figure 2, two spheres tied with a string, and rotating at an angular rate. Because of the rotation, the string tying the spheres together is under tension. Figure 3, exploded view of rotating spheres in an inertial frame of reference showing the centrifugal forces on the spheres provided by the tension in the tying string. Inertial and non-inertial reference frames can be distinguished by the absence or presence of fictitious forces, as explained shortly. The effect of this being in the non-inertial frame is to require the observer to introduce a fictitious force into his calculations. Sidney Berwitz and Lorentz Einstein in A Contemporary View of Elementary Physics, page 138. The presence of fictitious forces indicates the physical laws are not the simplest laws available, so, in terms of the special principle of relativity, a frame where fictitious forces are present is not an inertial frame. The equations of motion in a non-inertial system differ from the equations in an inertial system by additional terms called inertial forces. This allows us to detect experimentally the non-inertial nature of a system. VIR Null, Mathematical Methods of Classical Mechanics 2nd edition, p. 129. Bodies in non-inertial reference frames are subject to so-called fictitious forces, pseudo-forces, that is, forces that result from the acceleration of the reference frame itself, and not from any physical force acting on the body. Examples of fictitious forces are the centrifugal force and the Coriolis force in rotating reference frames. How then are fictitious forces to be separated from real forces? It is hard to apply the Newtonian definition of an inertial frame without this separation. For example, consider a stationary object in an inertial frame. Being at rest, no net force is applied. But in a frame rotating about a fixed axis, the object appears to move in a circle and is subject to centripetal force, which is made up of the Coriolis force and the centrifugal force. How can we decide that the rotating frame is a non-inertial frame? There are two approaches to this resolution. One approach is to look for the origin of the fictitious forces, the Coriolis force and the centrifugal force. We will find there are no sources for these forces, no associated force carriers, no originating bodies. A second approach is to look at a variety of frames of reference. For any inertial frame, the Coriolis force and the centrifugal force disappear, so application of the principle of special relativity would identify these frames, where the forces disappear, as sharing the same and the simplest physical laws, and hence rule that the rotating frame is not an inertial frame. Newton examined this problem himself using rotating spheres, as shown in Figure 2 and Figure 3. He pointed out that if the spheres are not rotating, the tension in the tying string is measured as 0 in every frame of reference. If the spheres only appear to rotate, that is, we are watching stationary spheres from a rotating frame, the zero tension in the string is accounted for by observing that the centripetal force is supplied by the centrifugal and Coriolis forces in combination, so no tension is needed. If the spheres really are rotating, the tension observed is exactly the centripetal force required by the circular motion. Thus, measurement of the tension in the string identifies the inertial frame. It is the one where the tension in the string provides exactly the centripetal force demanded by the motion, as it is observed in that frame, and not a different value. That is, the inertial frame is the one where the fictitious forces vanish. So much for fictitious forces due to rotation. However, for linear acceleration, Newton expressed the idea of undetectability of straight-line accelerations held in common. If bodies, anyhow moved among themselves, are urged in the direction of parallel lines by equal accelerative forces, they will continue to move among themselves after the same manner as if they had been urged by no such forces. Isaac Newton, Principia Carolari 6, page 89, in Andromeda translation. This principle generalizes the notion of an inertial frame. For example, an observer confined in a free-falling lift will assert that he himself is a valid inertial frame, even if he is accelerating under gravity, so long as he has no knowledge about anything outside the lift. So, strictly speaking, inertial frame is a relative concept. With this in mind, we can define inertial frames collectively as a set of frames which are stationary, or moving at constant velocity with respect to each other, so that a single inertial frame is defined as an element of this set. For these ideas to apply, everything observed in the frame has to be subject to a baseline, common acceleration shared by the frame itself. That situation would apply, for example, to the elevator example, where all objects are subject to the same gravitational acceleration, and the elevator itself accelerates at the same rate. In 1899, the astronomer Carl Schwarzschild pointed out an observation about double stars. The motion of two stars orbiting each other is planar. The two orbits of the stars of the system lie in a plane. In the case of sufficiently near double star systems, it can be seen from Earth whether the perihelion of the orbits of the two stars remains pointing in the same direction with respect to the solar system. Schwarzschild pointed out that was invariably seen. The direction of the angular momentum of all observed double star systems remains fixed with respect to the direction of the angular momentum of the solar system. The logical inference is that just like gyroscopes, the angular momentum of all celestial bodies is angular momentum with respect to a universal inertial space. Applications. Inertial navigation systems used a cluster of gyroscopes and accelerometers to determine accelerations relative to inertial space. After a gyroscope is spun up in a particular orientation in inertial space, the law of conservation of angular momentum requires that it retain that orientation as long as no external forces are applied to it. 59. Three orthogonal gyroscopes establish an inertial reference frame, and the accelerators measure acceleration relative to that frame. The accelerations, along with a clock, can then be used to calculate the change in position. Thus, inertial navigation is a form of dead reckoning that requires no external input, and therefore is immune to jamming. A gyrocompass, employed for navigation of seagoing vessels, finds the geometric north. It does so, not by sensing the Earth's magnetic field, but by using inertial space as its reference. The outer casing of the gyrocompass device is held in such a way that it remains aligned with the local plumb line. When the gyroscope wheel inside the gyrocompass device is spun up, the way the gyroscope wheel is suspended causes the gyroscope wheel to gradually align its spinning axis with the Earth's axis. Alignment with the Earth's axis is the only direction for which the gyroscope spinning axis can be stationary with respect to the Earth, and not be required to change direction with respect to inertial space. After being spun up, a gyrocompass can reach the direction of alignment with the Earth's axis in as little as a quarter of an hour. Newtonian Mechanics. Classical mechanics, which includes relativity, assumes the equivalence of all inertial reference frames. Newtonian mechanics makes the additional assumptions of absolute space and absolute time. Given these two assumptions, the coordinates of the same event, a point in space and time, described in two inertial reference frames are related by a Galilean transformation, where R0 and T0 represent shifts in the origin of space and time, and V is the relative velocity of the two inertial reference frames. Under Galilean transformations, the time t2, t1 between two events is the same for all inertial reference frames, and the distance between two simultaneous events, or, equivalently, the length of any object, vertical bar R2 R1 vertical bar, is also the same. Special relativity. Einstein's theory of special relativity, like Newtonian mechanics, assumes the equivalence of all inertial reference frames, but makes an additional assumption, foreign to Newtonian mechanics, namely, that in free space light always is propagated with the speed of light c0, a defined value independent of its direction of propagation, and its frequency, and also independent of the state of motion of the emitting body. The second assumption has been verified experimentally, and leads to counterintuitive deductions including time dilation, moving clocks tick more slowly; length contraction, moving objects are shortened in the direction of motion; relativity of simultaneity, simultaneous events in one reference frame are not simultaneous in almost all frames moving relative to the first. These deductions are logical consequences of the stated assumptions, and are general properties of spacetime, typically without regard to a consideration of properties pertaining to the structure of individual objects, like atoms or stars, nor to the mechanisms of clocks. These effects are expressed mathematically by the Lorentz transformation. Where shifts in origin have been ignored, the relative velocity is assumed to be in the direction, and the Lorentz factor is defined by. The Lorentz transformation is equivalent to the Galilean transformation, in the limit z0, a hypothetical case, or v0, low speeds. Under Lorentz transformations, the time and distance between events may differ among inertial reference frames. However, the Lorentz scalar distance s between two events is the same in all inertial reference frames. From this perspective, the speed of light is only accidentally a property of light, and is rather a property of spacetime, a conversion factor between conventional time units, such as seconds, and length units, such as meters. Incidentally, because of the limitations on speeds faster than the speed of light, notice that a rotating frame of reference, which is a non-inertial frame, of course, cannot be used out to arbitrary distances, because at large radius its components would move faster than the speed of light. General relativity. General relativity is based upon the principle of equivalence. There is no experiment observers can perform to distinguish whether an acceleration arises because of a gravitational force or because their reference frame is accelerating. Douglas C. Giancoli, Physics for Scientists and Engineers with Modern Physics, page 155. This idea was introduced in Einstein's 1907 article Principle of Relativity and Gravitation, and later developed in 1911. Support for this principle is found in the Eötvös experiment, which determines whether the ratio of inertial to gravitational mass is the same for all bodies, regardless of size or composition. To date, no difference has been found to a few parts in 1011. For some discussion of the subtleties of the Eötvös experiment, such as the local mass distribution around the experimental site, including a quip about the mass of Eötvös himself, see Franklin. Einstein's general theory modifies the distinction between nominally inertial and non-inertial effects by replacing special relativity's flat Minkowski space with a metric that produces non-zero curvature. In general relativity, the principle of inertia is replaced with the principle of geodesic motion, whereby objects move in a way dictated by the curvature of spacetime. As a consequence of this curvature, it is not a given in general relativity that inertial objects moving at a particular rate with respect to each other will continue to do so. This phenomenon of geodesic deviation means that inertial frames of reference do not exist globally, as they do in Newtonian mechanics and special relativity. However, the general theory reduces to the special theory over sufficiently small regions of spacetime where curvature effects become less important, and the earlier inertial frame arguments can come back into play. Consequently, modern special relativity is now sometimes described as only a local theory.